Hi everyone, welcome to the third video in the inverse trig function series. This final video will be over integrals. You can see the objectives listed here: finding the antiderivative of trig functions, what do you need to know, comparison of similar integrals, and finding the antiderivative by completing the square. Okay, basic trig functions, the integrals of trig functions. We need to know these two cold. We need to know that the integral of sine u du is negative cosine u plus c. We also need to know that the integral of cosine u du is sine u plus c. Those you need to know cold, absolutely cold. So here are the ones that you can derive. So the first one is tangent. So let's write tangent x dx. I'm going to switch to the x just to make this a little less confusing. If I rewrite this, I could rewrite it as sine x over cosine x dx. Letting u be cosine x, du would be negative sine x dx, which we have in the numerator except for the negative. So this would be, if I used u substitution, negative 1 over u du. And that would get me negative the natural log of, cosine x, and then plus c, which is the formula. But if you can't memorize the formula, you could actually derive the formula that way. And then you could do the same thing for the integral of cotangent u. Right? If you did that, you would end up with basically the natural log of sine x this time, because the sine would be in the denominator, plus c. So those two you could actually derive. Now, the ones that are harder to derive would be the ones that you would have to learn because you can't integrate them easily. And so that would be the secant u du, which would be the natural log of the absolute value of secant u plus tangent u plus c. And then, of course, the integral of cosecant u du, which is negative natural log of cosecant u plus cotangent u plus c. All right? So these cold, these you can derive, these you'll have to learn or at least look up. So once again, on the integrals of trig functions, you really only need to use one of each pair. And so on the integrals, we'll use the sine, the tangent, and the secant, just like we did for derivatives. So once again, because we are using the integral, the opposite of the chain rule in a derivative is going to be u substitution. And write these formulas down because we will be using these in most of our problems because we will be using u substitution. Once again, sine, inverse tangent, and inverse secant only because the other three are very similar to this one. Okay, so when we see something that looks like this, we have the dx over the square root of something squared, we're going to start to think that perhaps this is the arc sine, right, plus c is what we're going to think of. But we need to look at here, and we can see here that u squared is x squared, so that would make u equal to x. And then we also know that a squared is equal to 4, so a is going to be equal to 2. Okay, and we'll take the principal root of this. All right, so what is du dx? Well, du dx of this would just be 1. Okay, so that would be du is 1 dx, which is satisfied in the integral. So, since the du is satisfied within the integral, and we know that the integral is going to be equal to the arc sine of u over a plus c, since I know what u and a are, then the integral is going to be equal to the arc sine of x over 2 plus c. And that's how that works. Okay, so on this next one, we see that there's no square root in the denominator. So this is probably inverse tangent. Okay, so inverse tangent is going to be 1 over a, arc tan, having a hard time writing that, arc tan, u over a plus c. So that's what we're after. So we need to look at what is u. Okay, so we say u, can't get that to right, u is equal to u squared is 9x squared. So u is going to be equal to 3x. Okay, a squared is equal to 2. So a is going to be equal to the square root of 2. All right, if I do du dx, or du is going to be 3 dx. So this needs a 3, right? And so it needs a 1/3 on the outside. And so to write this, I would say I've got my 1/3 that I'm bringing down times 1 over a, arc tan, u over a, u is 3x over the square root of 2, plus c. That's it. I'm just following the formula. Once you determine what u and a are, you make sure that your du is satisfied, then you can just write out the equation. So this next example looks an awful lot like arcsecant, and so you can kind of see here what it looks like. And so I'm going to go to the inside. I'm going to identify u squared. U squared is 4x squared. So u is 2x. Du is 2 dx. So I've got all that done. A squared is 9. So a is 3. I notice that I do not have either u. I don't have u and I don't have du. So I can't quite finish this until I do something to it mathematically. So I'm just going to rewrite this problem just a little bit. So I've got dx, and then I have an x, and then I'm going to rewrite this as 2x squared minus 3 squared. Okay, and then I know that I'm going to need this to be a 2 because that's u, and those need to be the same, right? So that this is u and then u squared. Then I also know that du needs to be satisfied, so I put a 2 here, right? And so I've noticed that since I've added a 2 over 2, do I need to put a 1/2 out here? No, because I've already put the 1/2 by making this a 2 down here. 2 over 2 is 1. I have changed its form, but not its value, and so I don't add anymore. So the du is satisfied. Now I have the u, everything is set up properly, and so I can just write my, it's going to be 1 over a, so 1 over 3, arcsecant of the absolute value of u, which is 2x, over a, which is 3, and then plus c. And that's my answer. Okay, this is a comparison of similar integrals. All right, you can kind of see, looking at them, that they look pretty similar. They each have something different. And I really, really like this example because this puts side by side problems that look very similar but use different methods to solve them. All right, so let's look at number 1. Number 1, if I tried to do u substitution, it would fail because u would be the denominator, x squared plus 9. And then so du would be 2x dx. There's no way to add an x. So this is not a u substitution problem. This is an arctangent problem where u squared was x squared. So u is x. A squared is 9. So a is 3. And so you would get, as you're doing this, because I've got the 4 dx in the top, right? So I've got the 4 on the outside. I would end up with 4 times 1 over a, arctan u over a plus c. So those are just like the problems that we had been doing before. Right? So notice that I have the x squared in the bottom, but no x term in the numerator. That is arctangent. That's an inverse tangent. Okay. Now this one, on the other hand, if I use the same idea here, if this is u, x squared plus 9, then du would be 2x dx. So that one can use u substitution. This is a u sub problem, right? So I could rewrite this one, and I would have, I would pull the 4 out, right? I would have a 2x dx over x squared plus 9. So this would be a natural log problem. So 4 times the natural log, 4 over 2, right? 4 over 2, natural log of the denominator plus c. So this would just be 2 natural log absolute value of x squared plus 9 plus c. Basic u sub. Okay. Now the final one, number 3, you see that on this one this was x squared but no x. This is x squared and an x, so the u sub worked. X squared and an x squared. Well, this one is a division problem, a long division problem. So as I divide the top by the bottom, right? So I have a 4x squared plus 36, and then subtract. Then I end up with 4 minus 36 over x squared plus 9. And then if I go to integrate that, this becomes rather interesting because I have, and let me do this, 36, 1 over x squared plus 9 dx, which this first part is really, really easy to integrate, right? It'll just be 4x when I get it finished. But this second part over here is an inverse. It's a tangent, right? Because u would be x, a would be 3, and so I would have 4x, I'm going to write it bigger over here, 4x minus 36, the 36 stays, over a, which is 3, and then I have the arctangent of x over 3 plus c. So that turns out to be 4x minus 12 arctangent x over 3 plus c. So this last one has a different technique to it. And I think this is really helpful to see the pattern and see them side by side and see what they look like. Okay, so the final 2 examples have to do with finding the integral by completing the square. And so let me just show you, this is one way. This is, of course, going to be the simplest way to do this. So I'm going to rewrite. I'm still in a rewrite. I haven't taken the integral yet. And I'm going to divide this up. I'm going to do x squared minus 4x, and then I'm going to put this plus 7 over here. Okay? And then what I'm going to do then is I'm going to complete this square. I take half the middle term and square it, so plus 4. But I can't just randomly add 4 without taking it away over here. Now, this is not the other side of an equal sign, so they have opposite signs because 4 minus 4 is 0. So I have not changed the problem, just its form. And so this is going to give me the integral dx of, and then I'm going to end up with x minus 2 squared plus 3. All right, so my u is going to be x minus 2. Du is going to be 1 dx, so it's already fulfilled. And then a is just going to be the square root of 3. And this is an arctangent problem. So this is, the integral is going to be 1 over a arctangent of u, which is x minus 2, over a, which is square root of 3, plus c. Okay, so this is still a completing the square problem. And so let's go ahead and rewrite this. So if I have the square root in the denominator, then it is sine. Arc sine is what I'm after. And so I'm going to write the square root symbol, and I'm going to move things around a bit. Okay, so I am going to have I'm going to factor out -1, okay, from this, and that's going to give me x squared plus 4x. Okay, so I'm going to leave that just like that. So I factored out a -1. I need to add 4 on the inside, and I need to and then I need to notice here that this is not adding 4, it is subtracting 4. So I'm going to add 4 to the outside. Now this is tricky. Take a second, take a look at this. All I did was factor out a -1. That's what this is. Rewrote it, left a little room, added 4 here. Okay, and then added. Notice that I wasn't adding 4 because I factored out the -1. This is really -4 and added 4. 4 minus 4 is still 0. So I'm going to rewrite it again, still the integral. And I have 4 minus, and then I'm going to factor this. It'll be something squared, x plus 2. Okay, so if I rewrote this again, I would have dx over 2 squared minus x plus 2 squared. That would mean that u is x plus 2, du is 1 dx, the du is satisfied, a is 2, and then this would be arc sine. So this will be arc sine of u over a plus c. And that's it for this video. Be sure you took good notes, and I will see you in class.